Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss bases and dimension. So in this topic, we will define a basis. We will show how to find a basis given a collection of vectors. We will see that if the span of two bases are equal, then both bases must have the same number of vectors. We will define the dimension of a vector space or subspace based on the number of basis vectors, and we will see now why we can call, for example, R3 a three-dimensional vector space. We will also then further go on to discuss the benefits of having an orthonormal basis. Now, first let's start with a definition. If a collection of vectors is linearly independent, then that collection of vectors is said to form a basis for its span. Now, recall that the span is all linear combinations of a collection of vectors. A basis, however, is simply that collection of vectors. So, given a vector space, a collection of vectors is a basis for that vector space if, first, the collection of vectors is linearly independent, and second, the span of those vectors is the entire vector space. Notice that a subspace can also have a basis as well. First of all, the collection of the vectors must still be linearly independent. However, the span of those vectors must simply be equal to all vectors in that subspace and nothing else. Now, we have already seen how we can determine if a collection of vectors is a basis. If we are given the collection of vectors u1 through un, if these are linearly independent, then they form a basis for the span of those vectors. How do we find this? These vectors are linearly independent if and only if the rank of the matrix U that is comprised of the vectors u1 through un forming the columns of U, if the rank of that matrix is equal to n. Of course, if these n vectors are in the vector space of either real or complex numbers r to the n, m, or c to the m, and where m is less than n, then these n vectors can never form a basis, because if you have 10 vectors in r to the 5, those 10 vectors cannot be linearly independent. If they cannot be linearly independent, they cannot form a basis. Also, given a collection of vectors u1 through un, we've also seen how we can find a subset of these vectors so that the subset is a basis for the span of those vectors. Again, we define the matrix U comprised of its columns being these n vectors. And what we did is we found a row equivalent matrix that is in row echelon form. If there are no free variables associated with any column, that is, all columns contain a leading non-zero entry, then the collection of these vectors forms a basis for their span. If, however, there are free variables associated with one or more columns, that is, there are columns that do not contain leading non-zero entries, all we do is remove the vectors corresponding to these columns, and the remaining vectors form a basis for their span. So, question. Do these 4 vectors in R4 form a basis for R4? And if not, find a subset that does. Well, if we create the matrix comprised of with columns comprising these 4 vectors, we find that it is row equivalent to the matrix on the right. As you can see, the 4th column is associated with a free variable as it does not have a leading non-zero entry. Thus, eliminate the 4th vector, and a basis for the span of these 4 vectors are the first 3 vectors. So the span of the 4 vectors is equal to the span of the first 3 vectors. The first 3 vectors are linearly independent, therefore the first 3 vectors form a basis for the span. Do these vectors form a basis, and if not, find a subset that does? Well, once again, we create the matrix U and we note that it is row equivalent to the matrix on the right. Columns 2 and 3 are not associated with leading non-zero entries, they don't contain them, and therefore are associated with or are free variables. Thus, we will eliminate vectors 2 and 3. Actually, you can see that vector 2 is a scalar multiple, 3/4 of vector 1, and vector 3 is also a scalar multiple of vector 1. Basically, it's half of vector 1. So by eliminating those 2 vectors, a basis for the span of all 4 vectors is simply the vectors 1 and 4. And if we were to take the span of only one of those vectors, it would not equal the span of both of them. So vectors 1 and 4 are linearly independent, and therefore they form a basis for their span. Do these form a basis, and if not, find a subset that does? Once again, we create the matrix comprised of these 4 vectors as columns, and we find a row equivalent matrix that is in row echelon form. We note that the rank of the matrix is therefore 4. There are 4 vectors. Therefore, these 4 vectors are linearly independent, and therefore they form a basis for their span. Thus, this is indeed a basis. Now, if we're in R to the m, if we consider the m vectors where the first has all zeros except for in the first entry, the second has all zeros except for in the second entry, and the kth has all zeros except for the kth entry, this is always going to be a basis. Because after all, if we create the matrix, this is a matrix that has ones all along the diagonal, and therefore this is already in row echelon form. Because it is an m by m matrix, therefore the rank of this matrix is m, and thus all m vectors above form a basis for their span. Now, given two different bases of a vector space that is either all of f to the m, where f is either the reals or the complex numbers, or a subspace thereof, then both of these bases must have the same number of vectors. Here's a sketch of the proof. Now, suppose U1 and U2 are a basis for a subspace of R3, and simultaneously V1, V2, and V3 are also a basis for that same subspace. Now, what that means is every vector in v1, v2, and v3 can be written as a linear combination of u1 and u2, while simultaneously u1 and u2 must be written as a linear combination of v1, v2, and v3. Well, for argument's sake, we're going to try to find how we can write v1, v2, and v3 as linear combinations of u1 and u2. Well, u1 and u2 can form the first two columns of this augmented matrix, while v1, v2, and v3 form the balance. If we were now to perform Gaussian elimination and just Gaussian elimination on this, we would end up with a matrix that looks like the following. Now, why is the bottom row all zeros? The bottom row must be all zeros because whether or not we chose v1 or v2 or v3 to be the target vector, the rank of the full matrix, the augmented matrix, must equal the rank of the 3 by 2 matrix. But the rank of the 3 by 2 matrix of the two u vectors is equal to 2, and therefore all of the vectors v1, v2, v3 must also be reduced to 2 rows. This must be true because we are able to write each of v1, v2, v3 as linear combinations of u1 and u2. Now that gets problematic because let's just memorize those row operations. Whatever row operations we did to that augmented matrix, let us now do the exact same row operations to this matrix containing only v1, v2, and v3 as columns. Well, the result's going to be the same. We're going to have at least one row of zeros. So no matter what the other values are, the maximum rank of this matrix is 2. But wait, we assumed that v1, v2, and v3 formed a basis, and therefore they must be linearly independent. But if we can write v1, v2, and v3 as linear combinations of u1 and u2, then this suggests they are linearly dependent. So if this suggests they are not linearly independent, but we assumed that they were a basis, and therefore they must be linearly independent, this leads to a contradiction, and thus both bases must have had, in this case, 3 vectors. Also, one thing that is nice about a basis is that every different linear combination of a collection of basis vectors defines a unique vector in their span. Identically, every vector in the span of a basis must have a unique linear combination of basis vectors that equals it. That is to say, if u1 through un is a basis, then given an arbitrary vector v, the system of linear equations defined by finding a linear combination of the basis vectors equaling this target vector either has no solutions, that is, v is not in the span, or it has one unique solution. Under no circumstances will there ever be infinitely many solutions. Definition. The dimension of the vector space that is the span of n vectors is said to be n. We will describe such a vector space as being an n-dimensional vector space. If the span of these vectors is a subspace, then we will also describe that subspace as being n-dimensional and having, of course, the dimension n. For example, we have already seen that every single vector in R3 can be written as a linear combination of these three linearly independent vectors. Thus, the span of these three vectors is all of R3, and because they are linearly independent, they form a basis for R3, and consequently the dimension of R3 is, as we would suspect, 3. Consequently, every basis for R3 must have three vectors. Also, therefore, every collection of three linearly independent vectors in R3 is in fact a basis for R3. So this is only one basis for R3. There are infinitely many bases for R3. Each of them will have three linearly independent vectors. This particular basis is called the canonical basis for R3. For example, if we consider the following two vectors in R3, we note that they are linearly independent, as one is not a scalar multiple of the other. Because they are linearly independent, they do form a basis for their span. Because there are two vectors, the dimension of the span of these two vectors is 2. The span is a plane in R3 that passes through the origin. Now, because there are only two vectors in this basis, it follows that the span cannot be all of R3. We're essentially guaranteed that. So basically, the span of these two vectors is a two-dimensional subspace of the three-dimensional vector space R3. For example, this is a single non-zero vector in R3, and it is therefore linearly independent. Trivially. Because it is linearly independent, it forms a basis for its span. That is, it is a basis for all scalar multiples of it. Sort of a trivial basis. Because there's only one vector, the dimension of the span of this one vector is 1. So the span of this one vector is a single line in R3 that passes through the origin. Because there is only one vector in the basis, this cannot span all of R3. Instead, it spans a one-dimensional subspace of the three-dimensional vector space R3. Now, we have already seen that these m vectors in f to the m, where f is either the reals or the complexes, are linearly independent, and therefore they form a basis of an m-dimensional vector space. However, every vector in f to the m can be written as a linear combination of these vectors. After all, given an arbitrary vector u is equal to u1 times the first vector in this basis, plus u2 times the second vector, plus u3 times the third vector, plus so on and so forth, up until um times the last vector in this collection. Thus, the span is all of f to the m. Thus, all bases for f to the m must have m vectors, and similarly, any collection of m linearly independent vectors in f to the m forms a basis for that vector space. This particular basis above, once again, is called the canonical basis for f to the m. Also, the span of any collection of n linearly independent vectors in f to the m, where n is strictly less than m, is therefore the basis of an n-dimensional subspace of f to the m. Now, two more definitions. First of all, if the vectors in a basis are all mutually orthogonal, that is, the inner product between any two vectors is 0, that basis is described as being an orthogonal basis. Similarly, if the vectors in an orthogonal basis are also normalized, that basis is described now as being an orthonormal basis. Now, here's a claim. Given a basis of n vectors u1 through un, if we perform the Gram-Schmidt algorithm on these n vectors to get n orthonormal vectors u1 cap through un cap, then the span of the original vectors equals the span of the orthonormal vectors. Now, this is because each original vector can be written as a linear combination of the orthonormal vectors, and because each of the orthonormal vectors is a linear combination of the original vectors, thus their spans must at least overlap. However, because they are both bases with the same number of vectors, consequently their spans must coincide or be identical. Thus, given one basis, we can always form an orthonormal basis for that same vector space or subspace. Now, the clearest benefit of having an orthonormal basis instead of simply an arbitrary basis is as follows. If V is in the span of a basis, we must solve a system of linear equations in order to find the coefficients. Also, if no solution exists to this system, then V is not in the span of this basis. Now, solving a system of linear equations is an expensive operation. We have to perform Gaussian elimination, and if we want to find the coefficients, then we also have to do backward substitution. Now, given an orthonormal basis, however, given any vector v, we can calculate a vector called the approximation of v, called v tilde, which is the inner product of v and each of the orthonormal vectors times the corresponding orthonormal vector. Essentially, v tilde is the sum of the projections onto each of the orthonormal vectors. Now, this is actually a very cheap operation as it only requires you to calculate n inner products. And that is not that difficult. As a bonus, v tilde gives you always the best approximation of v of any vector that is in the span of the orthonormal basis. That is, v tilde is closer to v than any other vector in the span of the orthonormal basis. If v tilde is equal to v, then that can only be true if v is in the span of the orthonormal basis. That's a nice result, and it's a lot easier to calculate the approximation v tilde than it is to actually solve a system of linear equations. So, following this topic, you now understand the idea of a basis for a vector space or a subspace. That is, a collection of linearly independent vectors, the span of which is that vector space or subspace. You can take a collection of vectors and find a subset that forms a basis for the span of the original collection of vectors. You know that all bases for a vector space or subspace must have the same number of vectors, at least for finite dimensions. You are aware also that orthonormal bases are better than arbitrary bases, and that it is much easier to work with orthonormal bases, as you don't have to solve a system of linear equations. You also understand that the span of a basis equals the span of the orthonormal vectors that result from the application of the Gram-Schmidt algorithm. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!